As an AV integrator, I've been riding the wave of the analog to digital transition for many years. I celebrated installing one of the early Crestron systems, long before it was called Crestron, replacing the giant multi-strand cables, Amphenol connectors, mechanical switchers, and relays with wireless control panels that could send digital control commands. Much better. The old systems didn't make any sense. After a career with Crestron and AMX, I joined Contemporary Research and experienced another revolution in video distribution. We created the first commercial-grade TV tuner to tune in the channels of the digital transition. And then 5 years later, we brought out the first commercial encoder modulator into the marketplace. In the past 2 years, we have transitioned that technology to also output streams over IPTV using networks for carrying the channels. Today, the analog era of composite, component, and VGA has transitioned to HDMI and digital video delivery systems, including AV switching, IP video switching, digital RF channels, and IP video streaming. All are way better solutions than what we've had in our analog past. All appear to be different, but they share a common foundation. In this course, we'll look at the underlying architecture of each system, how they're alike, and how they differ in application, codecs, and integration. The video delivery systems we use in integration divide into two basic applications. One is presentation, where you're presenting live presentations where the switching has to be zero and going from one source to the other, and latency between your mouse interactions and audio has to be as close to zero as possible because the audience is in the same room as the presenter. So that includes AV switching, which these days are typically based on HDBASET, and IP switching, which is based on Motion JPEG 2000 technology. The category I call distribution is designed for more wide area distribution of video streams. The two ones most commonly used in commercial applications would be digital RF, which uses MPEG streams, and IPTV, which uses the same MPEG streams. This is also the same technology that you use on your Roku box, Amazon Fire TV, web videos. They're all in that category where it's designed to have very small streams with very good quality, presented over an extremely wide area of distribution. In terms of the consumer stuff, that's over the world, over the country. In commercial, you're usually distributing that over a facility. All of those are actually AV over IP solutions. All of them stream AV through Ethernet packets and employ encoders and decoders. All use category cable or fiber for signals. RF can use fiber or category cable, but primarily uses coax to deliver the signals. All compress video to some extent, especially for 4K, and all switch video streams to the desired destinations. AV switches that used Cat5 to carry signals weren't very reliable for many years until HDBASET was developed. It operates just like a standard conventional AV switch did. However, it's actually based on IP technology. So you have, in one enclosure, you have central encoders and an IP switch inside. And that switch distributes control, Ethernet, and video through packets. It's based on 10 gigabit transmission, but the packets don't carry Ethernet data. As some of the older systems, it can go up to 300 feet, 100 meters, over unshielded twisted pair, shielded twisted pair, or fiber wiring. 4K over Cat5, 6 untwisted, may be limited to about 35 to 70 meters. You can get more with Category 6A cable or shielded Cat6 cable. Proprietary chipsets are used to transmit the signal and then decode the signal at the other end, much like an IPTV system. But there's good interoperability between systems and different brands. HDBASET is still a popular choice by integrators wherever you have a conventional AV switch application. HDBASET 1.0 can handle up to 4K 60 420. When you have signals greater than that, you would move to HDBASET 2.0 systems that compress the higher values of 4K, so that an 18 gig 4K signal is compressed down to 6 gig, as systems from control system vendors include interactive RS-232, IR control, and other features native to the control system. Units that have pass-through 232 or infrared control require an external control system. In addition, you would generally use Cat6 shielded twisted pairs, mainly because when you take, it's all a 10 gig system, so they recommend you don't take the cables next to each other in a bundle for the next 20 meters, and you try to keep everything random. If you go to, in most cases, Cat5, Cat6 cable can work. However, they have a lot of restrictions on how you run the wires with UTP cable. You don't want those cables run as a bundle together because noise can definitely be a factor, because again, you're using PAM16, so there's a lot more things that can come in. So you have noise from the adjacent cable, noise from other foreign sources can affect the quality of that signal and cause problems or reduce the distance that you can go. So many integrators, when they're installing a system, use Cat6 cable or 6A cable to eliminate the problem with noise over distance and adjacent cables. Whenever you plug in an Ethernet cable, you're connecting to a modulator, which sounds kind of surprising, but that's how signals are carried across everything, over radio waves, coax, cell phones. So the digital signal has to be modulated and carried onto waves so that the data can travel long distances. For Ethernet uses pulse amplitude modulation, and all that means is that you have a set of waves, hills and valleys, and you divide that up into different levels so that, for example, PAN5 that drives 1 gig Ethernet, that signal level is broken up into 0, +1, +2, and then for the valleys, -1 and -2. With added encoding, it creates an XY grid for data, so you have data on one aspect and data on another aspect, and all 4 pairs carry data across, giving you 1 gig Ethernet. Now for 10 gig, which includes HDBASET, they use PAM16, so you're evaluating 16 levels of waves and arranging the information in a large checkerboard format. The center square, by the way, in 10G systems is used for 2.5 or 5 gig networking, something that you don't see yet, but is becoming more prevalent if you look on products having the ability to accept 10 gig as a network feed and then divide that into 1 gig, 2.5, or 5 gig over Cat5e6 cable. Now, the enemy of PAM is noise, either caused by adjacent feeds of wiring or foreign noise that's coming from some other source. Now, Cat5e and 6 can transport 1 gig signals relatively safely. However, you'll notice that Crestron, when they sell their cable, is always providing cable that is shielded. 10 gig should use this category 6 shielded or 6A7 cable. The difference being is that category 6 shielded has a foil around standard Cat6 cable. 6A, the individual pairs are also shielded, so within the cable the pairs are shielded from themselves. And yes, modulation is a fact. As a matter of fact, QAM that's used in RF, digital RF, is an equivalent technology of PAM. It's just used for one-way communication, where PAM is designed for two-way communication. IP switching systems are designed to be the IP equivalent of HDBASET. In this case, we separate the switch out, use a standard conventional IP switch in the center with encoders at the start and decoders on the other side. This way you can have any kind of combination of encoders or decoders, inputs and outputs within the system, and you can easily add to and extend the system at a later date. All are based on some version of MPEG encoding. It's called Motion JPEG 2000. It's a stream composed of individual compressed JPEGs with audio and control and other features added. Because you have individual frames, there's very little latency switching from one stream to the other stream. And there's actually three compression platforms. One is 10 gigabit systems, and they're mathematically lossless, is the term used, generally using a 3-to-1 compression scheme. So again, that 18 gig is being compressed down to 6. 1 gig systems are based on keeping with standard 1 gig network cable, standard 1 gig network switches. Saves a lot of effort. You can use Cat6, Cat5e cable, and that image is compressed to 20-to-1, which gives you a virtually lossless, which just means you can't really see the difference between the original and the compressed image. There's also one system that limits the 4K signal to 4K 60, 420, and compresses all the video 8-to-1. So you still have the value of 1G wiring with limits on the level of 4K signal you can put through the system. You're going to need a dedicated network because the streams are definitely more robust than a normal in-house data network can handle. And these systems are often brandified by different variations of JPEG encoding and names. So you'll see brands like Pixel Perfect, Pure 3, even SVDOE. They'll call it a custom system, but strangely enough, the compression schemes come out exactly the same, and Motion JPEG 2000 is a free codec, so there's no reason to create some new kind of system when the codec you need to switch is already free. The benefit of IP switch integration is that you have a lot of flexibility for inputs and outputs. There's a lot of different ways of configuring the system. You have transceivers that can be defined as an input and output. All you need is a 1 gig or 10 gig multicast switch in between. And systems from control vendors offer advanced features. Often you have KVM capabilities, local HDMI switching, adjustments for video wall presentation. Other units are out there that have pass-through RS-232 or infrared. For there you need an external control systems, and very often there's a little Linux server you have to get to enable a control system to talk to the transceivers in the system. I really can't verify what's best, 10G, 1G, can you see the difference? And I think each integrator has looked at that and made their decisions based on the quality that they get. I'll do some predicting that I would think you're going to see some options for 2.5 and 5G networking sometime in the future, because then the guys who are doing 1G, all they're doing is just changing the compression in the signal, and now you can have the same system that was 1G move up to having maybe 10-to-1 compression instead of 20-to-1 compression. Motion JPEG 2000 is pretty much like it sounds. It's a stream made up of individual JPEG 2000 streams, compressed to fit the need of the network. It was originally designed for archiving so that films could be stored in less space without losing original quality, and for video production, again, having smaller files, the ability to go back to the original and switch between frames for video switching applications. Recently, with larger networks, 1 gig and 10 gig network capabilities, JPEG 2000 has come into its own as a way to switch images for a video system. The larger bandwidth streams used for a 10 gig system are about 6 gig, using 3-to-1 mathematically lossless streams. In other words, they could be converted back to original format if used. 1 gig systems, the compression is about 20-to-1, giving you a frame that's 0.8 gig or 800 meg stream for 4K. Again, in the marketplace, you have some just call it Motion JPEG 2000. Others will more brand it, such as Pure 3 with Extron and Pixel Perfect in Crestron, and other companies also are using Motion JPEG 2000, but they don't call it such. But if you look at the compression rates and how it works, it's going to be Motion JPEG in the background. MPEG was created to have very high compression to simplify video distribution over RF, IP, and having excellent quality with high compression. So the original ones were MPEG 2, then MPEG 4 came out, and now we have H.264, which is just a bit more advanced version of MPEG 4. The concept behind MPEG is that it's called an interframe encoding system, where not every picture is a JPEG. So the stream consists of a group of pictures called the GOP. The first picture is always a JPEG. The remaining frames described what changed. So they compare each other to say what moved, what colors changed, location changed, and it constantly compares the images with each other to get the best possible emulation of an actual moving picture. That results in very high compression rates. So H.264 can take a 1080p stream that's 3 gig and knock it down to a 15 megabit stream. HEVC, which again you'll see more in consumer applications, not in commercial, mainly because the codecs aren't in chipsets yet. It's still developing, and it's quite expensive for use for commercial facilities. But that'll reduce it about 400-to-1 or more. So the images you see, if you have 4K on your Apple TV or Roku box or Amazon Fire, that's going to be 4K, HEVC or Google standard, which is similar, highly compressed, also a lot of stuff taken out. It's probably 420, it's probably 24 frames. They compress it as much as possible so that they can easily transport over your network. Now, for commercial uses, the latency for MPEG, for us and many others, is about a half second. That's the goal you want for commercial, so that in a stadium, there's not a huge delay for the viewer between the action going down at the venue and the football field and what you see in the skybox. And the problem that MPEG over IP has had typically is that a lot of losses and time delays are taken up by the network. So you're not at 500 milliseconds. You're actually at, in some locations, an 8-second delay, which I would call a poorly done system, but still, it can be a much longer display where RF is instantaneous, and that's kind of the difference between how MPEG is used between RF and IP. At Contemporary Research, we look at MPEG over RF and MPEG over IP as two sides of the same coin. So our modulators and encoders can process video as an H.264 stream and output it as a modulated channel over RF, or output it as an IPTV stream to go over a network, or both at the same time. The only difference is in IP, we put some identifiers to give it a network address for use by multicasting. Now, H.264, MPEG 4, is very efficient. Typically, you can compress video up to 200-to-1, so that a 3 gig 1080p stream can be streamed at 15 megabits per second. Now, when programs are output for RF, 2 full HD programs can be carried by one RF channel. That's where you see RF channels as 2.1 and 2.2. That's where that comes from. It's one MPEG stream with 2 programs. For IP, we send each program out individually because that's more efficient for internet applications. For RF, TVs already have a built-in decoder. It comes free. So, and TVs made in the past 2 or 3 years can also play 1080p as well as 720p and 1080i. For IP distribution, need a decoder attached to each display, as TVs don't generally have a true commercial IP TV decoder inside. The one big advantage about MPEG distribution is that it's open platform, so that you could have MPEG 4 streams coming from the cable company that you pay for per month. They can be distributed through RF and IP, and you can also mix in in-house streams. The point is, these standards are very open platform, not really proprietary as we saw in IP switching. So it doesn't matter whose encoder created the stream. It doesn't matter what brand of TV you have, they'll play it back. If you have an MPEG 4 IPTV decoder, it'll play back any kind of streams that are usually MPEG 2, MPEG 4, or MPEG 4 HEVC. They can all play them back. For RF distribution, a modulator creates the MPEG stream and then formats it to carry the stream over a specific channel, from channel 2 to channel 135. All those channels are combined and broadcast together over one coax cable. There's no switch in between. It's the TVs that are the switch. They change the channels at the destination end. We make a system called Display Express that combines 3 aspects for control right through the coax that carries the TV channels. There's web-based software called Display Express, where you can use web-based forms to create control panels, presets, names for devices, names for channels, and you can freely create your own sequences and management over the web without needing a custom control system. At the same time, you could use Crestron AMX, Extron control systems to create your own custom commands as well. In the middle, instead of a switch, there's the display control center, and that receives the commands over IP or RS-232 or USB and formats them into a control channel that's distributed through the RF network. At the end, there's a little box that goes on each TV, and one is called the ICC1232, the other is called the IRX. Both of those have the control codes inside the box, so you're not sending Samsung-specific, LG-specific control codes. You're sending generic control commands to the boxes, and they know what to send to the TV to make it work. So for programmers, once you program a system and you save the code, you don't care whether it's Samsung or LG for the next project. You can save the code, reuse it for the next project, and swap out TVs freely and just change the code that's inside the box. At Contemporary Research, we don't expect that every integrator is an expert in RF design and installation, but we have people who are. So we can work with you, look at the specs, help design a system, look at how to do the RF runs, calculate levels that we're going to hit the TVs, create a specification, and help you make a proposal for the system that you're going to install. And we can also recommend a coax cable and splitters. We don't sell those, but we can recommend plenty of people who do. One way we can really simplify the integration process is we have a prepackaged system called VenueVision. So this is a good example to follow. You could do the same thing with individual components, but this is simplified because we've done everything for you. All of the encoders are pre-programmed to like channel 2.1, 3.1, 4.1, and so on. And they're all connected and pre-wired to a combiner. And we have the control center, and that's pre-programmed. And all the controllers you have, their address is preset. We've already done that for you. We've installed the control settings that you need for what kind of TVs and the brand and make and model of TVs you're controlling. So everything's pre-engineered. All you really have to do is take that rack kit out of the box, set it on a table, plug it in, and plug the output to your RF output for the system. From there, you can use the internal web page, which we've preset. So we have the basic 8 channels already set up on the system. We've done number the TVs from 1 through 20, and you can go on from there. And then you can go and change names. So you can name the channels to what fits that installation. You can name the TVs. You can group the TVs and whatever grouping works out for you. So now you have a place to start, and you have a fully working system, and you haven't done anything yet. So you can take the controllers, which are pre-labeled with their address, and through the software or just a spreadsheet, and give it a name. This is going to be the front entry. This is going to be this TV over here. And so you can identify where the TVs are located, name those in the software, name that in a spreadsheet, whatever you want to do. And then as you install the controllers, you can actually use that web page on a laptop and go ahead and test the TVs as you install them. So by the time you're done, you know it already works. There aren't any questions. If something doesn't work, you know, okay, it is working. So, did I forget to screw in one connector? Is the power off on the TV? Things like that. So troubleshooting this system becomes very simple. Now, if you do have, say, a Crestron or AMX control system you want to use, no problem. Both of those can coexist. So you can go into the Ethernet port, you can go into the 232 port and start writing your code. But as you're writing, you still have the web page to fall back and to test and see, okay, that didn't work like I expected. Okay, let me do that with the control buttons. Okay, yes, it's working. I missed something in my code. So you can troubleshoot your code as you work. The math that we use for designing the system is not really all that complicated. So I'll break down this system that we have as an example. Let's say we do have 8 channels that we're using, which is really 4 of the encoders. So we'll feed those into an 8-way amplifier combiner. So which then I can have 8 of those encoders, so that you could build this without much change into, say, a 16-channel system. Very easy to do. The output of that will total 32 dB. It's actually 232 dB MV. That's what you would see in a meter, but this is good enough for math. And then that feed would go to an 8-way splitter, which will feed 8 separate runs to the TVs. Then you have 4-way splitters at the end of those runs, and each one of those feeds 4 TVs. So you're doing a total of 24 TVs. And let's say your worst case run is, say, 400 feet. Because we don't look at the total amount of coax that you're using in the entire system. All that matters in RF is, what's my worst case? So you measure how long it takes to get from the system out to the TV approximately, and work on your worst case scenario, because that will have the most loss, and all the rest are going to have more power available to them. So let's say this drops 8 dB, which in this case we're figuring at, over 400 feet, we lose about 2 dB per channel, because we just have really 4 channels in this system. So that's -8. So when you subtract all the losses, that means each TV is going to get about 7 dB. and we like to put our thumb on it. You can easily use 0 as the perfect number and go plus 10 or minus 10, but we always like to have a little more power than 0, so if something isn't wired there or something isn't wired there, we lose a little bit. It doesn't really matter. The TV itself works fine with minus 10 to plus 10, and we find many sets like LG, I can hit those TVs a lot harder. Most TVs don't like RF levels above 15, so that's why we try to stay under 10 in our basic design. And that's it. So the usual response we have when we work with dealers on their first installation is like, is that it? I'm done? And that they call me back after, well, okay, that didn't take long at all. Mainly because we've taken out the variables in the system. And that's a great starting place for a guy doing an RF installation. RF is still a preferred way to distribute video signals over very large venues and small venues because of the simplicity of integrating the system and the low cost. So you can start out with something simple at a worship center, placing 6 or 7 TVs out to the facility, running RF cable, coax to each one of those, and then using the software and the display controller to manage everything throughout the system. You could even start without a control system because all you really need at the TV side is an infrared remote if they want to change channels. So you could start really, really simple and then expand that out. Usually, say for a church, they're going to take the live feed and distribute that within the facility, and then a second channel with signage saying today's events, things like that, going to other TVs without the system. Another advantage of RF is that locations near the sanctuary can use coax for the connection. Now, obviously, there's going to be that half-second delay of MPEG. If that's crucial to them, they can retask the coax and put SDI signals to those TVs and have complete interchangeability with the audio that's in the sanctuary and the one in the TVs in the entrance to the sanctuary. But you can go large scale as well. That's where it really plays out. We have a lot of stadiums that looked at spending millions for a massive IPTV rollout, and then they realized it's TV. So it comes to us over cable channels. Why not use the same cable channels and distribute those without having to go through the step of IP? So you have major sites like the Superdome, Tampa Bay Buccaneers, Seahawks, and many other locations and college locations mix channels provided by DirecTV, Dish, or the cable company, and then do a few in-house live feeds throughout the facility, making it very inexpensive to create channels, information, entertainment, and then live video throughout the facility. And all they need is a little box going to each TV. The only network connection is at one point talking to our Display Express software, and also in many facilities there's a control system with touchscreens in different areas to also manage the areas for like sports bars and things like that within the facility. That way, as far as the finance, they can leverage RF for an inexpensive way to deliver video streams to TVs and use the Ethernet to manage TVs through control touch panels in the skybox, or distribute Dante audio to different areas within the facility. And they're also looking forward to going to 4K because an RF channel does not care what it's carrying. So you can take a 4K HEVC stream from the studio at the site, put that on an RF channel, and if you have smart TVs, they already have HEVC decoders built in. So it's a very easy way to gravitate to 4K where it's needed within a facility. Now, over the years, we've seen a lot of large scales installed handled by major companies like Haivision, things like that, where a group has to come in, set up the network, manage the encoders, decoders, servers, and all of that. Generally a fairly expensive high-end system that goes in a corporate center. But today, more and more sites are taking a more open platform view towards doing IPTV, using a standard MPEG encoder and mixing that with MPEG channels from cable companies as well, and then managing all that with a custom control system. For us, we look at Display Express being an integrated RF and IP system. We can do both at the same time, IP only, RF only. It doesn't really matter to us. The Display Express software can actually send the commands directly over the network itself. So if you have a system that's strictly IP based, all you need is a PC that's running the software. The Display Control Center receives commands from the custom system or Display Express, and then it can route both of those the commands to RF ports and to IP ports and knows the difference between the two. So you can have a custom control system do IP system or use Display Express, and you can identify locations that are on the RF, locations that are IP. All you care about is you're sending commands and the system figures out where they should be routed. In our system, with the QPID that we have, it's kind of designed more for integration. You don't need, like RF, you don't really need to start out with a control system if you don't need it. You can pick the little box inside the room by the video projector or display. It can have an onboard channel list that can update over the network with the free app. And you can control that locally with a simple IR remote, and you're done. Or you can integrate the controller through RS-232 with your local control system in the rooms. You can also talk to the box through the in-house network and command it that way. Inside every controller is a built-in library of RS-232 or IR control. And there's a library inside. All you have to do is send it a number to know it's supposed to talk Sony infrared or Samsung via 232, LG through 232. The codes are already on board the controller itself. So integration is fairly simple because the code's already done for you. It can be controlled in simple ways, or you can extend it out for local control, or you can see, again, IP commands through the RF that we use for RF through Display Express, or again, Crestron system, AMX system, do a custom system. It doesn't really matter to us. The platform's open. The nice thing is that you don't have to get super custom. You don't have to send specific Samsung commands. If that Samsung turns into an LG, you just send a number to the box and poof, it's sending LG commands now instead of Samsung. In RF, all the streams are sent at the same time over the same cable. Networks need stream management so that we're not streaming all the streams, only the streams that people want to see at that particular time. So the technology behind that is called iGIMP, which is called an Internet Group Multicast Protocol, to manage the streams and how they're used. So if you have a multicast switch, you would go to the software and enable multicasting, and then you would enable what's called the querier in the switch. Both need to be there. And the way the process works is that you have the decoder, usually referred to as the host, asks for a stream. And that format we're showing 239.27.0.27. There is a special group of addresses within network technology that is called the multicast group. So it means that whenever somebody asks for that, it becomes a destination. I want to see that stream. You ask for that number, and then that gets delivered to your host or decoder. What's going on in the network is the querier is always sending out messages over the network to find out if anybody wants to see a stream. The switch that the host is connected to has been looking at its ports and asking for a request. So it replies that, yes, I have a device that wants to see that stream. The switch then sends the stream to the switch, and the switch sends the stream to the port. And if several people at the same switch want to see the same video, it simply makes a copy rather than sending the new stream all the way from the origination point back to the switch. And then you have a leave message when you leave the stream, and there's a query that always goes out that says, anybody want to leave? Anybody want to leave? And the switch will say, yes, I have somebody. And then it'll turn off the stream at that particular port when it sees the message. So that's how multicast is working. The main point is that used to be something really difficult to set up. Now it's relatively easy within manufacturers of switching to enable multicast. One of the easier ones is Cisco. They have a very nice method of doing it. Other ones have their own techniques. The interesting thing is you often have to look for the manufacturer like us or some other vendor to tell you how to set up the switch. Oddly speaking, manufacturers will never tell you how to set it up. They assume you know. So one of the jobs of Crestron, AMX, and us and other people that do it is to send you instructions on how the system should be set up, because, like I say, the manufacturer, oddly enough, will never tell you or take responsibility for the setup. But generally, it's pretty simple to do, not a big deal as it used to be. Now let's look at installing an MPEG IPTV system using the same example we had before in RF. We have an alternate version of Venue Vision called IP, logically enough, that instead of an RF combiner, it has a 24-point PoE plus Luxel switch. And there's 20 IPTV decoders, that QIP-D decoder we talked earlier about. We will do many of the same steps that you would do if you were just buying the system as components. The first thing we do is set the switch for multicast and turn on the querier so we have the messages going back and forth between the systems. Then we set the decoders to static addresses and set the control type, what type of make and model of TV that you want to have. If when you take the system and you decide you want to use a router and go DHCP, the controllers work perfectly fine in that system, because when we're using our protocol, we are talking to a device number. So we're sending the broadcast out, say number 598, do this, or all of you do this. And each box knows its identity, hears the broadcast, and does what it's supposed to do. So the address of the unit isn't all that important in the way we do things. But if you have a custom control system and you need to talk with those devices directly, you would want static. But we set up with static because the system we send out doesn't have a router. So there is no DHCP. So this way you have a system you can start with and modify as you want later on. Then, as we have an application called CR Toolkit, that when you run it, it will find all those controllers on your network. It also finds the encoders on the system as well as that display controller. So it sees all the IP-ready components in your system. Then you can go to those and set up an address. Typically, you'd take one of the controllers, set up the channel list you want to have. In our case, we would already have a list set up for you, but you can just go there and set up a list. So these are the 8 programs you're going to have in the system, and putting in the multicast addresses and what channel number you want to assign to that. Then you can copy that to all of the other encoders. So we have to do the first one. And then you copy the application to the rest of them. They all know what the channel list is. And at that point, even if you didn't have a control system, you can use an IR remote and change channels just like it was a TV. Here, since we have the web application Display Express Lite in there, you can select a TV, change channels, turn it off, and it will turn off the display it's connected to as well, and set volume. So you have control over that system through the web page. And like before, as you start installing these units into the system, you've given them a name and you give the channels a name. Then when he installs it, he can take his laptop or an iPad if you're on Wi-Fi, and then test the system, change channels, and see if everything's working properly. So he can test as they go, or once it's installed, then you can go there through the web page and do that. So even if you're using a Crestron system or an AMX system, Extron, whatever, you can make sure the system is working and test it out as you're writing the software and compare that with the code that you write. So it really makes it quick to find bugs in your program, things like that, when you're installing a system. Use the page that's in there. We have some applications using that. And again, we're totally happy if you want to control the system through your Crestron system, AMX system. You could use our Display Express software, and then you've got presets and more advanced features than the small application inside. But all of that is the process you're going to use pretty much for every system that you install for IPTV. Well, that's it for this course. I think we've covered all the ground we can within the time allotted. Thank you for listening. Thank you for participating. I've really enjoyed putting this course together, trying to simplify the decisions that we have to make in all these different video systems that we have. There's so many brands and so many terms that confuse things, when actually there's only a certain amount of basic foundations that all of these systems use, so we can focus on what is the best for application, what special features do they offer as opposed to some other system. And altogether for us in the integration business, digital technology has been a great innovation for the solutions that we in the integration business can offer. It wasn't that long ago we were struggling with analog delivery systems where the type of wire twist was a big consideration, where if you ran the wrong wire, you could only use this brand of system, and you have to rewire and take another system if you had that. Limitations to distance depending on resolution. So many other issues that we had to deal with in the past have been resolved by technology. So it's a great time to be in the business, and we have a lot of great solutions we can choose from, and at least hopefully we have a better idea of what's happening under the hood of the different systems that we use. Thank you.